Welcome back to Think Design Works Smart. I'm Alex Bolboaca and I'm coming to you from the Mozaic Works studios. And today I'm recording after a meetup that took place last evening. It's a Friday. I will publish this video tomorrow. And in this meetup, I gave a talk about microservices. You'll find the link in the description. The talk and conversations were in Romanian, but if you would like me to record the talk in English, I'd be happy to. But going back to what happened is I made the point that the experience of the industry with microservices has shown that we need to understand and focus on the things that don't change and master the fundamentals of software development in general. Use those things and build upon those. And so I thought today to go a bit deeper into this, particularly because I've seen during the conversations that there was a bit of confusion on what are fundamentals. And so I will not talk about all the fundamentals of software development. That's obviously would be a very long talk, possibly a very long book. But what I like to show is examples of the way we think, of the way of going back to the fundamentals and thinking about what's always and what is and what will always be important for software development. And so I build this thing and we'll go into it little by little. First of all, let's look at the thing that we are trying to explore, and what we are trying to explore is what doesn't change in programming and in software development in general, but I will focus for now on programming. Of course, software development is more than that. It's programming, it's organizing teams, it's structuring large architectures over long periods of time, and so on. So there's a lot more there. But we'll focus on here on programming just to show to you how we find the fundamental things that don't change, that haven't changed for a very long time. The first thing that hasn't changed is that we write and modify code. And this is the fundamental activity that we are doing. And now code is mostly text today. Maybe it will be something else, but it will still be a variant of code. Code needs to be extremely precise, and one advantage of text over anything else is that it is very flexible. And maybe at some point we'll end up with writing or producing reusable modules that you just assemble and maybe are just a bunch of icons and have a different visual language on top of them. But until then, and this will probably take a long time, we'll still write and modify code that is text. And code has to work, right? These are two fundamental things. You can write code that doesn't work. It's actually pretty easy, but it has no value other than maybe amusement, being funny. So we write and modify code, and code has to work. If code has to work, what does it come from here? Well, we need to validate that the code works. And we can do it in a way that we used to do, like writing the code and giving it over to a tester that would validate that it works, and then getting back a list of bugs and then fixing those, and then repeating the cycle a number of times. And we've learned in time that this is not the most efficient way of doing this. Instead, the most efficient way of doing this is to validate that it works immediately after you write it. Now, there are various ways of doing that. You run it and you test it manually. You can go with the debugger through it. But the one that is most efficient, once again, is automated tests, because automated tests are like a debugging session that is saved. You have gone through the debugging and saved all the validations that you are making. This is fundamentally what automated tests can be compared to. All right, and then we write and modify code. So because of this is not a single instance, right? So we write the first code, and then 2 weeks later we need to modify that code, and then 2 months later we need to modify the code, and so on. So then if we want to be able to modify it, we need to write it so that we understand it later. So in a way, we need to project to our future selves. And notice that I'm assuming here that we are working alone, right? I'm not mentioning the team. If you are working in a team, you would not only write it so that you can understand it later, but that you write it so that you and your teammates can understand it later. And maybe any other programmer that joins the team in the meantime. So then how do we do this? Well, code is mostly naming, and naming is very important. If you find good names, then those will be easy to understand later on. But then the next thing is the structure of the code. How complicated is it? Do you have 4 or loop statements inside conditionals, and inside the loops you have another conditional that has another loop inside? This becomes very difficult to understand. So then there's a whole area of things that you look at regarding this need, that you need to understand this later. And you might think that when you write the code, let me put it this way, when you are writing the code, you are the smartest and the most knowledgeable you will be about that code. The more time passes, the more information, the more knowledge you will lose about the code. You'll forget about it. So don't assume that if you understand it today, you'll understand it in a month. That's one of the biggest challenges. You need to dumb it down today so that you can understand it in a month, because in a month you won't have the same knowledge about it that you have today. And this is why we need to follow things like naming and clean code, and actively look at making the code so simple that you can understand it at 3 a.m. if you get called to fix something. Right. So this is one example. Right, so this is the whole, and even if you replace, let's say you don't use clean code, you use some other set of rules, fine. But although I believe that clean code is very fundamental, I mean, no matter what rules you use, there will need to be some rules about methods, about objects, about classes, about the content of methods, like what do you have inside, how do you use loops, how do you use the conditionals, and so on. And many of the rules of clean code are just meant to simplify things, like don't mix conditionals with loops. because it's harder to understand. It's more likely that you will start making mistakes when you change this. Don't have loops inside loops unless it's very, very clear what's happening there. Don't introduce a lot of paths through your method. That is something you can measure using cyclomatic complexity. Don't have methods that are very long, because the longest your method is, the hardest it is to understand. It's better to group larger pieces of code into smaller things that are named, because this is how we understand things. This is for humans, right? We understand things by naming them and abstracting things away. Like we are talking about a bank, and if I'm telling you I'm gonna withdraw money from my bank, you'll know it's not the bank from the park, but it's more likely the bank from, well, in English is bench, but I think in Romanian is the same word. And you'll not make this confusion. And even when I'm saying bank, that's a highly complex institution, right? But I'm not interacting with everything there is in that institution precisely because it has a name and a very clear meaning. I know it has something to do with money, whatever they are doing, and so I can interact with it based on money, and we can talk about it in these terms. Same with code. Good names for methods are better, even if the behavior is quite complex, it's still helping a lot. So a lot of these things related to understanding are about raising the level of abstraction so that we don't have to think about all the details when we are discussing about that. Okay, another observation. Code becomes harder to change in time, and anybody who has written larger pieces of code understands this. First, you can write basically scripts, things that are maybe even a few hundreds lines long. They can be in a file. They can even be line by line, so without any particular organization or methods or so on. If it's one thing, it has a name, you know what it's doing, and it's fine. But the moment you keep adding to this, it becomes harder and harder to change, and this is rigidity. So how do we deal with this? Well, two ways. We want to organize the code such that it is easy to change. And when we find rigid code, we want to reorganize it such that it is easier to change. So how do we organize the code such that it is easy to change? Well, we have a bunch of heuristics, and we are calling those design principles. We are saying, like, look at low coupling, high cohesion, solid principles, Unix design principles, and maybe there are others, but these are the most used ones. Now, the problem with heuristics is they don't apply everywhere, then don't always apply the same. So there's a lot of thought involved here. And because there's no clear rule, you will still, even if you're following this, you will still create code that is difficult to change. Probably less than without thinking about it, but you'll still do that because it's in the nature of things. You'll miss out things. So what else can we do? We can continuously check that the code is easy to change. how do we do that? Well, the best thing to do is to test the changeability. How do you test the changeability? Well, how about having, if you have a class, having a second client for that class? You have one in production, you could have a second one, and those are tests, right? And we are going back to tests. Tests are a second client for the code. And if you learn how to read the signs, it's about reading the signs. So it's again kind of sensing things. Maybe you have a good sense for heuristics, but you might also get a good sense for reading the signs that are in tests about the rigidity of the code. So here's an idea. How about we write the test first? Because if we write the test first, we can test for the rigidity in a continuous manner, in an incremental manner. While we write the code, we also test for the rigidity of the code. So not only are we making the code working, which is what we needed to do anyway, we are also testing for this. So reorganizing rigid code so that it is easier to change. So you found a piece of code that is rigid. We can reorganize it, and that process is called refactoring. And this is an incremental process. It needs to be done in small steps and so on, because we need to keep the code working. This is part of refactoring. After every small step, you can validate that it works. So how do you refactor? You need to have tests. You modify a piece of code, you run the tests, when you are happy with it, you write another test, you check for rigidity, you make sure that it works, you check for rigidity, refactor. So we fix immediately when we find code that's hard to change, and the combination of all of these things is test-driven development. So this is one reason why I think this is a pretty good case that test-driven development is a method. It doesn't necessarily offer the special advantages, but it combines a lot of advantages from many methods into one efficient package, and actually effective package. But of course, TDD, you need to learn it, right? So this is about code, but how about the problem? And I will stop after this, because I think it's important to try and think about things in this way and go to principles, figure out what are things that are fundamental. Another thing that is fundamental, code has to solve a real problem. And we know the real problems are fuzzy, partially known, and they evolve in time. So actually, when your clients or product owner or whomever, product manager, comes with a problem to you and says, okay, let's implement this in our code, this feature in our product and so on. You implement it, and then through the process of implementing and through the process of seeing the feature in your product, this creates new ideas. So actually your problem will change in time. So real problems are fuzzy, partially known, and they evolve in time. You don't have full information about the problems that you are solving, and more than that, they will mutate. This is just the nature of the knowledge work. You get more ideas, and ideas mutate. So what do we do with this if you're trying to solve a real problem, but the problem can change? Well, how about figuring out what is the most valuable? or the most fundamental or the core part of that problem. So split a problem into smaller problems and solve each of the problems in turn, get feedback, and figure out what to do. And this is something that I'm calling incremental thinking. And here, actually I said ATDD, TDD, but the correct thing would be to mention also, probably to start from user stories or any other type of functional splitting, right? What I mean by this is the same process happens at this level. You get a problem is formulated as a user story. You split the user story into smaller stories, right? For each stories, you figure out which are the acceptance tests. You write one test for each acceptance criteria. You then solve each acceptance criteria with small cycles of TDD. And this is why we do all these things, right? So you see how this brings me to things that don't change in programming. And I think this is the fundamental idea that I'd like to talk about today. Just sit down and think really hard about what doesn't change. We know that programming languages change, right? When we first started software development, we had other programming languages. We had assembler, then Fortran, COBOL, and then we got into C, and later on into C++, Java, Python, .NET, JavaScript, and you have a bunch of language families. And maybe another thing that doesn't change is that we have fundamentally two approaches. One of them is functional, so immutability and focus on functions as a first class citizen. The second one is focus on objects, and objects are a first class citizen. And the third one is what actually happened, which I like to call class-oriented programming, where we focus on classes instead of objects. But so programming languages have changed, paradigms have not. We are using the same paradigms that we have been using for a very long time. Like object-oriented programming is since, 70s, and functional programming is since the 50s. So fundamentally, the programming languages might change, but we have the same fundamental issues. Now, an interesting exercise of imagination is this. What happens with AI? What can AI do? Right? So the AI, right now, if you go to ChatGPT and ask it to solve a problem, it can probably give you a partial solution to your problem. I've seen this, okay? So it spews out code that maybe, hopefully, kind of works. Now, the problem with this is that maybe you solve the writing problem. Let's assume it just works. But unless it also writes the tests, you cannot validate that it works. So you need to test it. Okay. And you can test it manually. You can go through it with a debugger. Still, the best way would be to write automated tests. But writing automated tests on code generated by AI, well, actually, on any code that is not yours is an interesting adventure. One that I personally like, but it's not particularly effective. We do it when we must. And then the second thing is, can you understand the code later on when you need to change it? Probably not, because you have not gone through the process of creating that code and then refining it until you get to the point where you can understand it 4 months later. So the problems are the same. The problems don't change. AI will fundamentally change programming once it can write code, it can validate that it works, it can modify the code. And then we just have to be sure that it can actually do these things. Because if we'll ever need to intervene in code written by AI, once again, that will be a very interesting adventure. One that I personally would enjoy probably, but would definitely be very inefficient. So AI for now doesn't solve these problems, right? And probably based on the fundamentals of AI will not fully solve this. Instead, what I'm thinking more and more is that we'll have assistants that are AI that will help us with the programming problems, but we still need to guide them. We still need to make sure that the tests are written and well understood. We need to make sure that we can understand the code. Because in order to be able to change it later. So yeah. So then maybe instead of writing the initial code, what we'll write is prompts for the AI to generate code, and then we'll modify it. Which is pretty much what many people are doing. I mean, doing Stack Overflow based programming is kind of the same thing. You go to Stack Overflow, you copy something, you modify it to fit your needs. And we've all done something similar to that. All right, so I'm not sure if this is the first part of a series or not, but maybe it is, because there are many other things that are fundamental and that don't change in architecture, in the way we organize teams, and also in the way we treat problems. So maybe it will be interesting to talk about those at a later date. But if you want me to delve deeper into this subject, please let me know in the comments. Thank you kindly for the watch, and until next time, remember to think, design, and work smart.